In this video, I'm going to show how we can first learn a deep belief net by stacking up restricted Boltzmann machines, and then we can treat that as a deep neural net that we fine-tune discriminatively. So instead of fine-tuning it to be better at generation, as we did in the previous video, we're going to fine-tune it to be better at discriminating between classes. This works very well and led to a big renewal of interest in neural networks. In speech recognition, it's had a major influence, and many leading groups are now switching to using deep neural nets in order to reduce the error rate in speech recognition. I now want to talk about fine-tuning these deep networks to be better at discrimination. So we first learn one layer of features at a time by stacking up restricted Boltzmann machines. Then we treat this as pre-training that finds a good initial set of weights in a deep neural network, and we fine-tune those weights using some local search procedure. In the previous video, I showed you how to use contrastive wake-sleep to fine-tune a deep network so that it was better at generating its inputs. In this video, we're going to use backpropagation to fine-tune a model to be better at discrimination. If we do this, it overcomes many of the standard limitations of backpropagation. It makes it much easier to learn deep nets, and it makes those nets generalize better. We need to understand why backpropagation works better when we pre-train the weights. And there's really two effects. There's an effect on optimization, and there's an effect on generalization. So the pre-training scales really well if we have big networks, especially if each layer has locality. So if we're doing vision, for example, and we have local receptive fields in each layer, then there's not much interaction between widely separate locations. And so it's very easy to learn a big layer more or less in parallel. When we do pre-training, we don't start backpropagation until we've already learned sensible feature detectors. And these feature detectors should be very helpful for discrimination. So the initial gradients are much more sensible than if we use random weights. And backpropagation doesn't need to do a global search. It just needs to do a local search from a sensible starting point. In addition to being easier to optimize, pre-trained nets exhibit much less overfitting. That's because most of the information in the final weights comes from modeling the distribution of input vectors. And these input vectors, if you're dealing with something like images, generally contain a lot more information than labels. A label typically only contains a few bits of information to constrain the mapping from input to output, whereas an image contains a lot of information which will constrain any generative model of a set of images. The information in the labels is only used for the final fine-tuning. And because by that stage we've already decided on the feature detectors, we're not squandering that precious information designing feature detectors from scratch. The fine-tuning only makes slight changes to the feature detectors we learned in the generative pre-training phase. And those are the changes required to get the category boundaries in the right place. The important thing is that backpropagation is not being required to discover new features, and so it doesn't need nearly as much labeled data. In fact, this type of learning works well when most of the data is unlabeled, because the generative pre-training can make use of all that data. The unlabeled data is still very useful for discovering good features. There is an obvious objection to this kind of learning, which is that when we do generative pre-training, we'll be learning lots of features that are useless for the particular discriminative task we want the net to do. Consider, for example, that you might want the net to discriminate between shapes, or you might want the net to discriminate between different poses of one shape. They need very different features, and if you don't know the task in advance, you'll inevitably learn features that are never used. When computers were much smaller, that was a serious objection, but now that computers are large enough, we can afford to learn features that are never used. And we can afford it because among all the features we learn, there will be some that are much more useful than the raw inputs. and that more than makes up for the fact that we've learned some features that aren't helpful for the particular task we're interested in. So let's apply this to modelling the MNIST digits. We'll now learn 3 hidden layers of features entirely unsupervised. Once we've done that learning, when we generate from the model, it will generate things that look like real digits. And it'll generate them from all the different classes, and it'll typically take a while before it switches from one class to another. And it will typically take a while before it switches from one class to another, because it'll tend to stay in the same ravine for a while before it jumps to another ravine. But the question is, are the features that we've learned that way useful for doing discrimination? So all we need to do is add a final 10-way softmax at the top and fine-tune it with backpropagation, and see if we do better than purely discriminative training. So here's the results on the permutation-invariant MNIST task. And what I mean by permutation-invariant is, if we were to apply a fixed random permutation to all the pixels, the same permutation to every test and training case, the results of our algorithm wouldn't change. That's clearly not true for something like a convolutional net. A convolutional net's been told something about the task. By applying this fixed permutation, we destroy all simple ways of telling the net something about the spatial structure of the task. So if you apply standard backpropagation, it's hard to do better than 1.6% errors. John Platt and myself have both tried quite hard applying standard backpropagation with various different architectures, and we're both quite good at doing it. You can actually beat 1.6% by using constraints on the incoming weight vectors of the hidden units. If you use an appropriate restriction on the length of an incoming weight vector, you can do a bit better than 1.6%. Support vector machines can get 1.4%, and this was one of the pieces of evidence that led to support vector machines supplanting backpropagation. If you pre-train a network using a stack of Boltzmann machines, and then you fine-tune it to be better at generating the joint density of digits and image labels, then you can get down to 1.25%. If you train a stack of Boltzmann machines and simply put a 10-way softmax on top and fine-tune it, you can get to 1.15%, and with more fiddling around, you can get that down to about 1%. So you can do a lot better than standard backpropagation, and also better than support vector machines, by using generative pre-training followed by discriminative fine-tuning. Marco Aurelio Ranzato, working in Jan LeCun's group, also showed, using a slightly different pre-training method, that pre-training helps for models that have more data and better priors. So they used an additional 60,000 distorted digit images, so they had a lot more training data. They also used a convolutional multilayer neural network, and Jan's group is the best group at tuning those. With backpropagation alone, they managed to get down to 0.49%. When they did the unsupervised layer-by-layer pre-training, followed by backpropagation, they got down to 0.39%, which at the time was a record. So you may remember this picture from the first lecture. This was one of the examples I gave of the success of neural nets. It's the same picture. And back then, I said we could get down to 20.7% by pre-training and then fine-tuning with backpropagation, and that the previous speaker-independent record on TIMIT was 24.4%, which actually required averaging several models. Li Deng at Microsoft Research picked up on this result immediately and collaborated on improving it, and this has led to a big change in speech recognition. If you look at this news story, it will refer you to a blog where the Chief Research Officer for Microsoft is talking about the big improvements in speech recognition caused by using deep neural nets.